In part one, we tackled the first 25 generative AI interview questions, the foundation every candidate needs. Now, in part two, we're stepping it up with the next 25 questions that dive deeper into real-world applications, advanced concepts, and tricky scenarios interviewers love to ask. Let's get you one step closer to acing that AI role.
What is a prompt in generative AI? In generative AI, a prompt is the input or set of instructions given to the model that guides what it generates. It can be as simple as a short phrase or as complex as a multi-part instruction with context, constraints, and examples. For example, in a text model like GPT, the prompt might be, "Write a 2-paragraph summary of the solar system in simple language." In an image model like DALL-E, the prompt might be, "A photorealistic image of a golden retriever surfing a wave at sunset." The quality, clarity, and structure of the prompt heavily influence the quality of the output. This is why prompt engineering, the art of designing prompts to get the desired result, has become a key skill in generative AI. Prompts can also include context, background information to ground the response, constraints, style, tone, length, or format requirements. Examples: few-shot prompting to guide the model toward a pattern. In short, the prompt is the bridge between human intent and AI output, telling the model what to generate and often how to generate it. How do you engineer or optimize prompts for language models? Engineering or optimizing prompts for language models is about designing inputs that clearly convey the task, constraints, and context so the model can produce the desired output with minimal ambiguity. Effective prompt engineering often involves these key practices. 1. Be explicit and specific. Clearly state the task, format, tone, and level of detail. For example, write a 100-word summary of this article in bullet points for a business audience. 2. Provide context. Give the model background information or reference material so it can ground its responses. 3. Use examples, few-shot prompting. Show the model sample input-output pairs so it can learn the desired style or structure within the same prompt. 4. Structure the prompt logically. Use step-by-step instructions or numbered tasks to help the model follow a sequence. 5. Iterate and refine. Experiment with wording, ordering, and detail until the outputs meet the quality standard. 6. Control output variability. Adjust decoding parameters like temperature, top K, and top P to balance creativity and precision. Prompt optimization turns a generic instruction into a precise recipe for the model, ensuring more consistent, accurate, and context-aligned results. What is in-context learning? In-context learning is the ability of large language models to learn and adapt to a new task during inference, purely from the examples and instructions provided in the prompt, without any changes to the model's weights. Instead of retraining or fine-tuning, the model is given task demonstrations directly in the input. For example, if you provide a few input-output pairs for translating English to French in the prompt, the model can immediately start producing French translations for new inputs in the same session. This works because transformer-based models like GPT store vast patterns from pre-training. The prompt acts as a temporary working memory, conditioning the model's predictions based on the context you supply. In short, in-context learning is learning on the fly, adapting behavior from the prompt itself, making LLMs extremely flexible for different tasks without additional training. Explain zero-shot, one-shot, and few-shot learning in the context of LLMs? Zero-shot, one-shot, and few-shot learning describe how much example guidance a large language model, LLM, gets in the prompt before performing a task. Zero-shot learning. The model is given only an instruction with no examples. It relies entirely on its pre-training knowledge. Example: translate "How are you?" into French. Comment ça va? One-shot learning. The model is given one example of the task in the prompt, then asked to apply the pattern to new inputs. Example: English, good morning. French, bonjour. English, how are you? Few-shot learning. The model is given a small number of examples, typically 2 to 10, in the prompt, showing the desired input-output pattern, then asked to generalize to new cases. Example: English, good morning. French, bonjour. English, good night. French, bonne nuit. English, how are you? In short, zero shot, just instructions. One shot, one example. Few shot, several examples. LLMs excel at all three because their transformer architecture and massive pre-training allow them to recognize and replicate patterns from minimal context. What are Retrieval Augmented Generation (RAG) systems? Retrieval Augmented Generation, or RAG, is a generative AI approach that combines information retrieval with language generation to produce more accurate, grounded, and up-to-date responses. In a RAG system, when a user asks a question, the model first retrieves relevant information from an external knowledge source, such as a document database, vector store, or search engine, and then uses that retrieved context as part of the prompt to the language model. The LLM then generates an answer based not just on its pre-training, but also on the most relevant retrieved facts. This solves two key problems with LLMs. 1. Hallucination. Reduces the risk of the model inventing facts. 2. Knowledge, freshness. Allows answers to reflect the most current data, even if it wasn't in the training set. Typical architecture. Retriever. Finds relevant documents, often using embeddings and vector search. Generator. Uses the retrieved context to produce a coherent, contextually accurate response. RAG is widely used in enterprise AI assistants, search chatbots, and domain-specific copilots because it blends the creativity of generation with the reliability of retrieval. Explain the concept and use of embeddings in LLMs. In large language models, embeddings are numerical vector representations of words, tokens, sentences, or even documents that capture their meaning in a way machines can understand. Instead of representing a word as a one-hot vector, which is sparse and doesn't encode meaning, embeddings place words in a dense, continuous vector space where semantically similar items are closer together. For example, the embeddings for king and queen will be close, and their vector difference can capture relationships like gender. In LLMs, embeddings are used at multiple stages. Input embeddings convert tokens into vectors before processing by the transformer layers. Positional embeddings add information about word order. Sentence document embeddings summarize larger chunks of text for retrieval or clustering. Use cases in LLMs and generative AI. 1. Semantic search. Find documents with similar meaning, not just keyword matches. 2. Retrieval Augmented Generation, RAG. Store embeddings in a vector database for fast context retrieval. 3. Clustering and classification. Group similar text or detect topics. 4. Recommendation systems. Match users with relevant content based on meaning. In short, embeddings are the language-to-math bridge. They translate meaning into numbers, so models can reason, retrieve, and generate intelligently. What are common metrics for evaluating generated text? Generated images. Evaluating generated content depends on the modality. Text and images require different metrics to capture quality, relevance, and diversity. For generated text, common metrics include Blue U, Bilingual Evaluation Understudy. Measures n-gram overlap between generated and reference text, often used in translation. Rouge, Recall-Oriented Understudy for Gisting Evaluation, focuses on recall of overlapping phrases, common in summarization tasks. Meteor considers synonym matching and stemming for better linguistic flexibility. BERT score uses contextual embeddings from BERT to assess semantic similarity. Perplexity measures how well a language model predicts a sample. Lower is better. Human evaluation judges fluency, coherence, factual accuracy, and style, often the gold standard. For generated images, common metrics include Inception Score, IS, measures both image quality and diversity using a pre-trained classifier. Fréchet Inception Distance, FID, compares feature distributions between generated and real images. Lower is better. Precision and recall for generative models separately measures fidelity and diversity of outputs. CLIP score measures how well an image aligns with a text prompt using CLIP embeddings. Human evaluation rates realism, creativity, and prompt alignment. How does Fréchet Inception Distance FID work? Fréchet Inception Distance, or FID, is a metric used to evaluate the quality of images generated by generative models by comparing them to real images in a feature space rather than pixel by pixel. Here's how it works. 1. Feature extraction. Both real and generated images are passed through a pre-trained Inception v3 network, used as a feature extractor. Instead of using raw pixels, we take high-level feature activations from one of its layers. 2. Distribution modeling. The features from each set, real and generated, are modeled as multivariate Gaussian distributions, each defined by a mean vector and a covariance matrix. 3. Distance calculation. The Fréchet distance, a statistical measure between two Gaussians, is computed. FID equals the absolute value of the difference between the mean of the first Gaussian and the mean of the second Gaussian, squared, plus the trace of the sum of the covariance matrices of the two Gaussians, sigma g negative 2, sigma r sigma g, 1/2, where mu r, sigma r, Schrodinger's mean and covariance of real images features, mu g, sigma g, Nurk's mean and covariance of generated images features. Fourth interpretation. Lower FID scores mean the generated images feature distribution is closer to the real images distribution, indicating higher realism and diversity. FID is preferred over older metrics like Inception Score because it accounts for both image fidelity and variety, and it penalizes mode collapse more effectively. What is the Inception Score, IS, and what are its limitations? The Inception Score, or IS, is a metric used to evaluate the quality of images generated by generative models by looking at both image clarity and diversity. But it does this indirectly through a pre-trained classifier. Here's how it works. 1. Pass generated images through a pre-trained Inception v3 network to get predicted class probabilities. 2. If an image is high quality, the classifier should output a probability distribution with low entropy, confident prediction for one class. 3. If the set of images is diverse, the marginal distribution of predicted classes across all generated images should have high entropy, cover many classes. 4. The Inception Score is computed as the exponential of the KL divergence between the conditional label distribution for each image and the marginal distribution over all images. Higher scores indicate better quality and diversity. Limitations: no comparison to real images. It doesn't measure how close generated images are to real ones, so it can't detect unrealistic artifacts if they still fool the classifier. Dataset classifier bias. It relies on the ImageNet trained inception model, which may misrepresent domains outside ImageNet's classes. Insensitive to mode collapse in unseen classes. If a generator produces high-quality images, but only for a few classes, IS can still be high. not universally applicable, works best for image domains aligned with ImageNet classes. Because of these limitations, IS is often complemented or replaced by metrics like Fréchet Inception Distance FID, which directly compares generated and real data distributions. How do you perform human evaluations for generative models? Human evaluation is essential for generative models because automated metrics often miss subjective qualities like creativity, style, emotional impact, or nuanced accuracy. The process involves structured methods to collect reliable feedback from human judges. A typical human evaluation pipeline includes 1. Define evaluation criteria. Common ones are quality or fidelity. How realistic or natural is the output? Relevance. Does it match the prompt or task? Diversity. Are outputs varied across multiple generations? Creativity or style for artistic or open-ended tasks. Factual accuracy for knowledge-based tasks. 2. Select evaluators can be domain experts for technical tasks or general crowd workers for broad consumer tasks. 3. Design the study format. Likert scale ratings. Example 1 to 5 score on realism. Pairwise comparisons. A by B testing between outputs from different models. Ranking tasks order multiple outputs by preference. 4. Sampling and blinding. Randomly sample prompts, dodge outputs, and hide model identity to prevent bias. 5. Statistical analysis, aggregate scores, run significance tests, and check inter-rater agreement, example using Cohen's kappa, to ensure consistency. Human evaluation is often combined with automated metrics, for example, pairing BLUE or FID scores with subjective ratings, to give a complete picture of generative model performance. Discuss the trade-off between sample diversity and quality. In generative models, there's often a trade-off between sample diversity and sample quality, because the same factors that make outputs varied can sometimes reduce their realism or precision, and vice versa. Sample diversity means the model produces a wide range of outputs that cover different modes of the data distribution. High diversity helps avoid mode collapse and is important in creative tasks, recommendation systems, or data augmentation. Sample quality means each individual output is realistic, coherent, and high fidelity. High quality is critical in applications like medical imaging, photorealistic rendering, or factual text generation. The trade-off arises because if you push the model to explore more, example is with higher temperature in LLMs or weaker discriminator pressure in GANs, diversity increases, but quality may drop, outputs can become noisy or less coherent. If you constrain the model for maximum fidelity, example is low temperature, strong adversarial filtering, quality improves, but diversity often suffers. Outputs may become repetitive or predictable. In practice, the balance depends on the use case. Creative generation. Favor more diversity, accept some drop in fidelity. Safety-critical or high-precision tasks favor quality, accept less diversity. Techniques like diversity-promoting loss terms, controlled sampling, and mixture of experts models aim to achieve both, but the trade-off is rarely eliminated entirely. How have you used generative models to create synthetic data? And what advantages does this approach offer? I've used generative models like GANs, VAES, and diffusion models to create synthetic datasets in scenarios where collecting or sharing real data was limited due to privacy, cost, or availability constraints. For example, in a computer vision project, we used a GAN-based pipeline to generate high-resolution images of rare manufacturing defects. Real defect samples were scarce, so synthetic images allowed us to train a defect detection model with better recall. In NLP, I've applied LLM-based text generation to create domain-specific Q&A datasets for fine-tuning chatbots, improving their coverage of niche queries. The advantages of using generative models for synthetic data include 1. Data augmentation expands the training set, improving model generalization. 2. Rare case coverage simulates uncommon scenarios, e.g., rare diseases, rare defects. 3. Privacy preservation generates realistic but non-identifiable data, aiding compliance with GDPR, HIPAA. 4. Cost and speed avoids expensive and time-consuming manual data collection. 5. Controlled variability allows adjusting parameters to target specific distributions or edge cases. In short, synthetic data from generative models can fill gaps, reduce bias, and accelerate AI development, provided it's validated to ensure realism and relevance to the target application. Describe your experience integrating generative models into user-facing applications. I've integrated generative models into user-facing applications by focusing on 3 pillars: model performance, user experience, and system reliability. For example, in a Microsoft Teams-style meeting assistant, I integrated an LLM with Retrieval Augmented Generation, RAG, to generate real-time meeting summaries and action items. The backend used Azure Cognitive Search for retrieval, an orchestration layer to structure prompts, and an LLM for final text generation. This ensured summaries were accurate, contextual, and aligned with the user's company data. In an image generation tool for marketing teams, I deployed a diffusion model with a guided prompt interface so non-technical users could control style, color palette, and resolution. I added safety filters for inappropriate content detection, output preview options, and caching for faster repeat generations. Key lessons from these integrations. 1. Latency management. Used batching, caching, and model distillation for faster responses. 2. User trust. Added transparency features like why this was generated and editable outputs. 3. Feedback loop. Collected user ratings and fed them into prompt and model tuning. 4. Scalability. Deployed models using Azure Kubernetes Service, AKS, for auto-scaling under high load. The result was applications that felt intelligent, responsive, and safe, while keeping the generative AI transparent and controllable for the end user. What special considerations are there for deploying generative models to mobile devices? Deploying generative models to mobile devices requires balancing model capability with the constraints of mobile hardware, user experience, and privacy requirements. Key considerations include 1. Model size and optimization. Mobile devices have limited memory and compute, so models often need quantization pruning or distillation to fit and run efficiently. 2. Latency. Users expect near-instant results. On-device inference must be fast, or heavy computation should be offloaded to the cloud with minimal round-trip delay. 3. Battery consumption. Generative models, especially large ones, can drain battery quickly. Optimizations and batching help reduce energy cost. 4. Connectivity. Offline or poor network scenarios require models that can run partially or fully on-device, with optional cloud fallback. 5. Privacy and security. On-device inference helps protect sensitive data, while encrypted communication is essential for cloud-based inference. 6. Model updates. Deployment pipelines must handle regular updates without requiring large downloads that frustrate users. 7. User interface design. Prompting, output editing, and result previews need to be intuitive and optimized for small screens. 8. Platform integration. Leveraging Core ML, iOS, TensorFlow Lite, or ONNX Runtime Mobile, Android, ensures compatibility and performance. In short, mobile deployment of generative AI is a trade-off between power and practicality. You need to deliver rich AI experiences while staying within the device's limits and maintaining user trust. How do you ensure real-time generation and low latency in production? Low latency is a full-stack problem. Model, retrieval, and infrastructure all have to be tuned together. Model and decoding right-size the model. Distillation, pruning, INT8 or 4 quantization, or a small specialist model for first pass. Fast decoding, streaming tokens, speculative assisted decoding, draft plus target model, small beam or greedy, KV cache reuse across turns, flash, page detention. Image/diffusion, latent diffusion, fewer scheduler steps, distilled checkpoints, classifier-free guidance only as high as needed. Context and retrieval, keep contexts short. Aggressive chunking plus re-ranking, dedupe and compress citations. Warm retrieval, ANN indexes in memory, per-tenant cache of top passages. Pre-compute embeddings, parallelize retrieval plus prompt assembly. Serving and infra-continuous batching or micro-batching on GPU. Pin big models in memory. Autoscale with warm pools. Region affinity edge serving to cut RTT. gRPC HTTP2. Keep alive. GuyZip. Avoid chatty hops. Caching. Prompt template cache. Logits cache for common prefixes. CDN for assets. Product tactics, stream results to the UI. First token less than 300 milliseconds, and progressively refine. Tiered quality. Fast draft. Refine if user lingers. Fall back to smaller model under load. Timeouts and circuit breakers with graceful degradation. Observability, track P50 or P95 or P99 end-to-end latency. Queue time versus compute time, cache hit rate, and token per second. A by-B guardrails on temperature/beam, and auto-scaling triggers tied to queue depth. Shrink the model, shorten the context, batch smartly, serve near the user, and stream early. Then watch P95 like a hawk. What are best practices for deploying generative models to the cloud? Cloud deployment of generative models equals treat it like a product, not a demo. Secure by default, observable, auto-scaled, and cost-aware. Architecture and serving use a stateless inference layer behind an API gateway. Pin models in GPU memory. Enable continuous batching and KV cache reuse. Pick the right runtime. VLLM or TGI or ONNX. Runtime or TRITON for high-throughput serving. Enable mixed precision and quantization, INT8 or 4. Separate concerns, retrieval or RAG service, prompt or orchestration service, safety service, inference service. Scalability and reliability, auto-scale on token or second and queue depth. Keep warm pools to avoid cold starts. Multi-region active or active with traffic steering. Blue-green or canary deploys. Shadow new models before promotion. Set SLOs or SLA, P50 or P95 latency, uptime. Add circuit breakers and graceful degradation. Fall back to smaller model or draft mode. Security, privacy, compliance. Private networking, VNet or private link. Managed identities, Key Vault for secrets, encryption at rest in transit. Data minimization. Don't log raw prompts or outputs by default. PII redaction. Configurable data retention and region residency. GDPR or HIPAA. Tenant isolation for enterprise use. Per-tenant retrieval indexes. MLOps and governance model registry with versioning, lineage, and signed artifacts. Pre-release eval gates. Quality, robustness, bias, safety, red teaming, regression suites for RAG and hallucination. A/B testing with offline plus online metrics. Rollout via feature flags. Performance and cost trim context, re-rank, dedupe, cache prompts, embeddings, and logits. Use speculative decoding, streaming tokens, and right-sized GPUs. Spot low priority with safe fallbacks. budget alerts and per-tenant spend caps, safety and trust content moderation, toxicity or PII filters, watermarking or provenance metadata, citations in RAG, uncertainty flags, and editable outputs to build user trust. Observability, trace end-to-end, P50 or P95 or P99, tokens or seconds, GPU utilization, cache hit rate, retrieval latency, structured logs plus distributed tracing correlation IDs, real-time dashboards and alerting. In short, isolate services, secure the edges, automate evals and rollouts, stream early, cache aggressively, and watch P95 like a hawk. Describe a challenging project involving generative models that you've tackled. One of the most challenging generative AI projects I worked on was building a real-time, domain-specific meeting assistant for enterprise clients, similar to Microsoft Teams Copilot. That could summarize conversations, extract action items, and answer follow-up questions based on company documents. The challenges were technical, operational, and user-facing. 1. Latency versus quality. Users expected near-instant summaries after a meeting ended. I implemented streaming generation for early drafts, with a background refinement pass for final summaries. KV cache reuse and speculative decoding brought latency down by 40%. Second, grounding in private data. Hallucinations were unacceptable. I integrated Retrieval-Augmented Generation (RAG) with an Azure Cognitive Search backend, using custom embedding models tuned for domain terminology, and added a citation system so every sentence could be traced back to a source document. 3. Scalability. The service had to support thousands of concurrent meetings. We used multi-region GPU clusters on AKS with auto-scaling, warm model pools, and load balancing to keep P95 latency under SLA. 4. Security compliance. Because of GDPR HIPAA concerns, all customer data stayed in region. I implemented tenant isolation, encrypted vector stores, and PII scrubbing before any inference call. 5. User trust and adoption. We built transparency features like why this was generated tooltips, editable outputs, and a feedback loop that retrained prompt templates based on user corrections. The end result was a system that delivered accurate, real-time, and compliant summaries, cutting post-meeting note-taking time by over 70%, while earning high trust scores in pilot deployments. How do you mitigate bias in generative models and outputs? Mitigating bias in generative models requires addressing it at 3 levels: data, model, and output, and continuously monitoring after deployment. First, data-level mitigation. Diverse and representative datasets. Ensure coverage across demographics, geographies, and contexts. Bias audits. Detect imbalances in source data before training. Data augmentation. Add underrepresented cases to balance distributions. Second, model-level mitigation. Debiasing techniques. Fine-tune with curated, balanced datasets, or apply adversarial training to reduce sensitive attribute correlations. Prompt conditioning. Guide model behavior using carefully designed system prompts. Fairness constraints. Integrate fairness-aware loss functions during training or fine-tuning. 3. Output-level mitigation content filters. Block toxic, discriminatory, or unsafe outputs before they reach the user. Re-ranking. Generate multiple candidates and choose the least biased or most neutral. Human in the loop. Use expert reviewers for sensitive use cases like hiring or legal summaries. 4th, continuous monitoring. Track fairness KPIs, post-deployment, e.g., demographic parity, sentiment analysis by subgroup. Implement feedback loops so users can flag biased outputs for correction. The key is treating bias mitigation as an ongoing governance process not a one-time fix. With technical, policy, and human oversight working together, what techniques do you use to identify and filter unsafe or inappropriate generation? I use a layered safety approach, combining pre-generation safeguards, post-generation filtering, and continuous monitoring to catch unsafe or inappropriate outputs in generative models. First, pre-generation, prevent at the source, prompt filtering and rewriting. Detect and modify risky user inputs before they reach the model. System prompt constraints. Embed clear content boundaries in the model's instructions. Fine-tuning/RLHF. Train with preference data that penalizes unsafe generations. Second, post-generation, catch before user sees. Content moderation models. Use classifiers, e.g. Azure Content Safety, OpenAI moderation, to detect hate speech, violence, sexual content, self-harm, or political extremism. Keyword and regex scanning. Simple but effective for known high-risk terms. Ensemble safety checks. Combine multiple detectors for higher precision. 3. Filtering and action block. Suppress unsafe responses entirely. Refuse. Return a safe refusal message. I can't help with that request. Sanitize. Redact unsafe elements while preserving usable content. 4. Continuous monitoring and feedback. User flagging tools. Let users report unsafe content. Safety dashboards. Track incidents by category and severity. Red teaming. Regularly stress test with adversarial prompts. The goal is to enforce precision, catch unsafe content without overly harming recall, allow safe creative expression, which means tuning thresholds, testing in production, and iterating constantly. How can training data curation impact model fairness? Training data curation is one of the most critical factors in determining a generative model's fairness, because the model learns patterns, including biases, directly from the data it sees. If the training set overrepresents certain demographics, languages, or viewpoints, the model will disproportionately favor those in its outputs. Conversely, underrepresented groups or scenarios may lead to poorer performance, stereotyping, or exclusion in generation. Even subtle imbalances, like skewed sentiment in product reviews or unequal geographic coverage in news, can encode systemic bias. Good curation practices improve fairness by ensuring representativeness, sampling data that reflects the diversity of real-world users and contexts, balancing distributions, augmenting underrepresented categories so the model doesn't overfit to dominant ones, removing harmful content, filtering out toxic, discriminatory, or historically biased language. Annotator diversity. Using labelers from varied backgrounds to reduce subjective bias in labeling tasks. In short, fair models start with fair data. And curation isn't just filtering, it's an intentional process of balancing, diversifying, and debiasing the input before the first token of training ever happens. How can differential privacy be used in generative AI? Differential privacy, DP, can be used in generative AI to ensure that the model learns general patterns from training data without memorizing or leaking information about specific individuals. In simple terms, DP introduces carefully calibrated randomness, usually as noise in the training process or outputs, so that the presence or absence of a single user's data doesn't significantly change the model's behavior. Applications in generative AI are 1. Private model training. Use DPSGD, differentially private stochastic gradient descent, to add noise to gradients during fine-tuning, preventing the model from memorizing sensitive records. 2. Privacy-preserving synthetic data. Train a generative model with DP so that any synthetic samples are statistically similar to the original dataset, but cannot be traced back to specific individuals. 3. Safe query handling. In RAG systems, apply DP noise to query logs or embeddings stored in vector databases to protect user information. Fourth, model output filtering. Apply post-processing DP techniques to ensure generated content respects privacy guarantees before delivery. The benefits are reduces risk of data leakage through model inversion or membership inference attacks, helps meet compliance standards like GDPR, HIPAA, and CCPA. In short, differential privacy allows generative AI to learn from sensitive datasets without exposing the people in them, enabling safe use in domains like healthcare, finance, and government. Describe approach to responsible AI in the context of generative models. A responsible AI approach for generative models means embedding ethical, safety, and governance considerations throughout the model's lifecycle, from design to post-deployment monitoring. 1. Design phase. Start with clear intended use cases and conduct risk assessments to identify potential harms, misuse, and fairness concerns early. Involve diverse stakeholders to capture multiple perspectives. Second, data curation. Build diverse, representative, and debiased datasets, removing harmful or toxic content and balancing underrepresented groups to improve fairness. 3. Model training and evaluation. Use bias detection pipelines, adversarial testing, and red teaming to identify unsafe behaviors. Apply techniques like differential privacy to protect sensitive information. Fourth, safety layers in deployment. Integrate content filters, refusal mechanisms, and watermarking. Give users controls over creativity level, style, or tone. Ensure clear disclosures when content is AI-generated. 5. Transparency and accountability. Document model capabilities, limitations, and known risks in model cards or system cards. Maintain audit trails for decision-making processes. 6th, post-deployment monitoring. Track fairness, safety, and factuality metrics in production. Enable user feedback loops and continuously retrain or adjust guardrails as risks evolve. In short, responsible AI for generative models is about proactive governance, continuous monitoring, and user empowerment, ensuring models are not just powerful, but trustworthy and aligned with human values. How do you audit and document the behavior of a deployed generative system? I treat auditing and documentation as a first-class part of the generative system. Everything must be observable, reproducible, and explainable from prompt to token. 1. Capture a complete privacy-safe audit trail, log request, retrieval context, prompt, model or version, decoding params, output, post filters with correlation IDs, store latency breakdowns, queue inference retrieval token counts and cost. Apply PII redaction, hashing, and data retention windows so logs are auditable yet compliant. Second, continuous evaluation in production. Maintain eval suites for factuality, toxicity, jailbreak resistance, bias by subgroup, relevance, faithfulness, RAG. Run online A/B and offline canary or shadow evals on the same traffic. Track P50 or P95 or P99, and hallucination rate via citation checks or claims verification. Flag drifts, input mix, retrieval quality, response lengths, safety scores. Third, reproducibility and lineage, version models, prompts, retrieval indexes, safety policies, and datasets in a registry. Every release has an artifact bill of materials, hashes, changelog, and rollback plan. Keep frozen snapshots of eval datasets and prompts to rerun audits verbatim. Fourth, governance and safety reviews. Pre-deploy risk assessment, intended use, abuse cases, user groups. Red teaming cycles with adversarial prompts. Document findings and mitigations. Change management. Approvals for model/guardrail updates with blast radius notes. 5. transparent documentation, publish model or system cards, training data sources at a high level, capabilities, limits, known failure modes, safety mitigations, and metrics bands, user-facing disclosures, AI-generated, citation, provenance in RAG, and watermarking or content credentials where applicable. Sixth, incident response and feedback loop, real-time alerts on safety regressions, circuit breakers to throttle or fall back to safer models. In-product report, chalk appeal channels. Triage queue feeds back into tuning of prompts, retrieval, and filters. What is transfer learning, and how does it enable better generative models? Transfer learning is a technique where a model trained on one task or domain is adapted for a different but related task or domain, reusing the knowledge it has already learned instead of starting from scratch. In generative AI, transfer learning is typically applied by pre-training a large model on massive general-purpose datasets. Example is DOT, internet-scale text, images, or audio, and then fine-tuning it on a smaller, domain-specific dataset. This enables better generative models because 1. Faster convergence. The model starts with a strong understanding of language, vision, or audio patterns, so it needs less data and time to specialize. 2. Higher quality outputs. Pre-trained models capture rich semantics and structure, improving fluency, coherence, and realism in generation. Third, data efficiency. Fine-tuning on a small curated dataset can yield high performance, even when labeled data is scarce. 4. Cross-modal transfer. Knowledge from one modality, example is text, can enhance another, example is image captions in text-to-image generation. 5. Domain adaptation. The model can be aligned to industry-specific language, style, or compliance requirements without retraining from scratch. In short, transfer learning lets generative models stand on the shoulders of giants, leveraging broad knowledge from pre-training and then specializing for targeted high-value use cases. What is meta-learning, and how might it accelerate generative model adaptation? Meta-learning, or learning to learn, is an approach where a model is trained not just to perform tasks, but to adapt quickly to new tasks with minimal additional data. Instead of optimizing solely for performance on a single training task, meta-learning optimizes the model's learning process itself. The goal is to produce an initialization or learning strategy that can be fine-tuned rapidly when given a small number of examples for a new task. In the context of generative models, meta-learning can accelerate adaptation by 1. Few-shot mastery. Preparing the model to generalize from very few task-specific examples, making it more effective for one-shot or few-shot prompting. Second, domain agility, allowing rapid switching between domains, example is medical writing to legal summarization, without full retraining. 3. Personalization, enabling quick alignment to a user's tone, style, or content preferences with minimal feedback. 4. Cross-task transfer, learning shared patterns across diverse generative tasks, translation, summarization, question answering, so improvements in one help others. Techniques like model-agnostic meta-learning, MAEAML, gradient-based meta-learners, and memory-augmented networks can be applied to LLMS multimodal generators to drastically reduce the cost and time of specialization. In short, meta-learning turns a generative model from a static tool into a fast-adapting collaborator, capable of tailoring itself on the fly for new contexts and constraints.
That's another 25 generative AI questions mastered, and your confidence just leveled up. Next, in Part 3, we'll tackle even more advanced challenges that separate great candidates from the best. Subscribe now and keep building your edge.